So welcome everybody to the second lecture for course Machine Learning. We will start with a bit of organization before we continue with our discussion of the main components of machine learning. And today we will also then start to discuss how to combine them. Yeah, so please, Pavo, go ahead.
Okay, yeah. So hi, everyone. Now, after these first few days of the course, we've been looking at, there has been some repetition in the questions in Slack, which is of course totally okay and unavoidable since there's such a large number of you. But we should still somehow try to minimize that repetition. And so I would just remind everyone that Slack has pretty decent search function. Now, in order for that search function to be effective, you still have to pay some attention on how you formulate your questions in Slack. So, for example, if you are asking a question about some specific assignment and task, you should start your question with, let's say, assignment 1, task 6, and so you could write A1.6. And you could maybe even, it depends on your question and whether it's possible or relevant or not, but you can even maybe add some keywords that make the search easier. And so, and if you are wondering what those keywords could be and how to formulate the question, just think how you should be searching for the answer to that question. And to the point, that's the way you should start asking the question, that first you try to seek for an answer already in the earlier threads. But of course, this does not mean that you have to rummage through, use an hour looking through all the channels and threads to seek an answer. So use your common sense. And it's totally fine that there is some repetition at times. And also, if we as TAs recognize that there is a repeated question, don't be surprised, we might just refer you to an earlier discussion. And in those cases, if you feel that the answer hasn't been, the issue didn't get clear to you, then you just return to the initial thread where you asked the question and ask for further clarification. And so, and if you are not familiar, and even if you are familiar with these kinds of search functions, I would recommend that you Google, look at some of the Slack blogs about how you can improve your searches. And there are all kinds of ways you can do all kind of filtering and such to make the search more effective. And so, but in any case, it's important that nobody starts to hesitate whether or not it's appropriate to ask your question. Always ask your question if something is unclear. So that's fine. And maybe finally, this is a bit of a side note, but you should think about the discussions and asking questions in Slack in a way that a sort of like a one measure of competence, especially in technical field like machine learning. One measure of competence is how well you can formulate and communicate technical ideas, and how well you are able to use appropriate terminology and so on. And so that to do it well in Slack is like a good practice for the project work and for the peer review also. And so, but that's all. Maybe we'll put some additional notes. I can write some additional notes in Slack in the general channel on what would be good practices in how to formulate the question. But just keep in mind that there are hundreds of you, so many questions have been probably asked before. Okay.
Thanks a lot, Pavo. Very helpful. So let me now quickly point out the assignments. So we have already released the assignment 1. Just to remind you, the course is built on 3 components. One component are the lectures like this one today. Second component, assignments, and third component, the machine learning project, which is maybe the main component or the meat of the course. But these assignments here, they are meant to help you getting grip or getting familiar with the tools that you might want to use in the machine learning project. So we have 9 assignments. These are very short, fast-paced assignments. So fast-paced in the sense you can complete them maybe in an hour. So if you work through the material, if you got used to how to use these Python notebooks, I think each assignment should be done in a few hours. However, maybe this is my prediction and the prediction is wrong. So we also learn on the way. But so currently we have assignment 1 running and the deadline is 21st of January. This means you have almost still 10 days. So there's no rush. We really want to start slow, that you get familiar with these coding assignments. And maybe the starting point would be to read carefully through all the material and information that we put here in this section, assignments. So here's the assignments instructions. There are also videos. And yeah, work through this. Then the next step could be to ask or to search for answers in the frequently asked questions. We now have frequently asked questions here. Where do we have them? Here. Frequently asked questions. Then if you don't find help here, you might go to Slack. If you don't find help there, you might send us an email. You find the contact addresses, the email addresses of our TAs here under Need Help. Yep. Okay. And yeah, you're also free to ask now questions during the lecture. The TAs will try to answer them on the fly. Yes, so let me now continue with the actual content of today, which is about the 3 main components of machine learning and how we combine them. So let me share my screen. Where do we have PowerPoint? Yes, so can you see my slides? Boom. Yes, thank you. Thank you. So we had the discussion of the basic principle of machine learning and decomposed it into 3 components. So the first component and maybe the main component is data. So we want to decompose data into data points which have features and labels. And now we need to practice this. So as a first guest speaker today, I have Esther. Esther, can you explain your data points?
Hi, can you hear me?
Yes, but we have an echo. So do you have...
Sorry. Do you hear me?
Yes, very good.
Okay. Well, one of my ideas for the machine learning project is to try to predict the price of a cryptocurrency other than Bitcoin. And for this example, I will use ADA.
Yes.
Well, in this problem, the data point would be some time frame, for example, 1 hour, 1 day, or even 1 week, depending on the trader's strategy. Well, the figures in my example would be the Bitcoin price and the fear and greed index. This last one is an indicator of market sentiment, and it is used to determine if a trend is going to end soon. For example, if the price rises a lot and the index is high or greedy, it means that the price will probably have a correction soon. And finally, the label is the ADA price, of course. And as we can see, there is a correlation between the Bitcoin price and the ADA's price. And in these charts, I have pointed out the uptrends and downtrends. And we can also confirm the direction of the price with the fear and greed index. But this is not an exact science, and there are times when it is not true. As we can see in some time period when Bitcoin goes up, but ADAS goes down. So this is just for, give a clue of how to operate or trade.
Thanks a lot, Esther. Very interesting problem.
Thanks.
So the next one would be Marco. Marco, please, what are your data points?
Yeah, so my data points, so this is about predicting future purchases of an individual customer or individual customers at a grocery store or whatever kind of store it might be. And one data point is one customer, and then the features are customer attributes like age, sex, purchase history, and location. These kinds of customer data. You can just anything you can think of, and the label is interest in some. So what you're trying to predict is interest in some possibly new or perhaps an old product.
Thanks a lot. And yeah, so this already touches one of the main application domains and the most, how should I say, productive applications of machine learning: recommendation systems. So think of customers in a very general sense. Like a customer could be a user on Tinder, on a dating app, and you would like to find out what would be interesting other dating app users that you could recommend, or on a job platform where a user should be presented interesting job ads. And I can only say this, for example, these two examples decided my current job and my current partner. So these recommendation systems, they have huge influence, at least on my life already. So the next one, Yasu.
Yeah, my data point was a canteen or a day in the canteen, which would contain features like how many people come there, how much food they take, and what the prediction target label would be how much food they need to make every day. Because the canteen serves different food on different days, they want to find out what is the optimal amount of food to purchase and make for each day, so that they have enough food to sell, but they don't have too much food left over after the day.
Yes, very good example. Thanks a lot. Then cows. Carlos, please.
Oh, thank you, teacher. So my data point is the second best animal in the world after humans, of course, a cow. The features is the quantity of milk produced per day or over time, or the temperature of the milk. And with that, you can label the cows by if the cow is sick or not, the species of the cow, the past peak production of the cow. You can also tell if the cow is sister of another cow. You can take the whole genealogy tree of the cow. So yeah, that's my data point.
Thanks a lot. Yeah, and you see already in this example, there are several labels. So there are 3 labels. This might be a multi-label problem. And also I want to point out here, yeah, the label, the quantity of interest is still a low-level property for a business problem or a business application. Sorry, could you turn off your microphone, Carlos?
I'm sorry.
Sure. So for example, the label, is it past its peak production? If this label is predicted as yes, then it's up to the business. What do we do with that cow? So it leads to decisions about the cow. Okay, then another example, Anne, could you maybe focus on this example from finance? What are the data points here?
Yeah, sure. So at least for me as a finance student, machine learning is the easiest to understand as a regression problem. And here in the picture, there's, for example, I'm trying to predict beta, so the systematic risk of an asset with respect to the market as a whole, or the slope of the line in the picture. So here the data points are daily observations of returns, and the features are in the y-axis, the excess return of the asset, and then in the x-axis, the excess return of the market. And then as the label, the quantity of interest is the beta. Okay, very interesting example, because here, when I first looked at this scatter plot, I would say, there's something a bit off, because I don't know this. The label should be something that is a property of each individual data point. But the thing is, these dots here do not need to be the data points that you consider. There's a big design freedom what you define as data points, and you could say this whole set of dots here, which are like daily observations, this whole set is one data point.
and you're interested in a property of this whole set of points, in this case, the slope of this regression curve. So this is then somewhat goes a bit one level higher, like meta learning. So a data point here would consist of smaller data points. But still, it's possible because, as I said, we use the notion of data point in a very abstract and versatile sense. This makes it very flexible, but you need to always be clear what is the data point. Okay, thanks a lot. Excellent examples. Did I forget somebody? Is there somebody still in the panelist room who wants to present a machine learning problem or data points? Okay, if not, we might organize. So I got a lot of suggestions. We might organize such a machine learning project workshop maybe next week or in 2 weeks, where we have one extra session beside the lectures, only dedicated to discussing such applications or machine learning project ideas. Okay, but now I would like to continue with the actual core content. So far we talked about two main components, which is the data. So we have data points. Each dot here in this scatter plot represents, for example, a day, and each day has a feature, the property, for example, the minimum daytime temperature or the current price of Bitcoins. And each day has also another property, which we call the label. Here, the y-axis or vertical axis, which is the quantity of interest, like the maximum daytime temperature, or in the cryptocurrency example, the price of another cryptocurrency. So we have data here, data points. The second component, what was the second component of machine learning? After data, what did we discuss? A model, and I use the term model in a very specific sense. A model is a set of different hypotheses, maps. So as soon as you have more than one hypothesis, you have a model. So this is a very simple model consisting of two different hypotheses. And machine learning is about finding the best hypothesis in this model or in this hypothesis space. That's what machine learning is about. But to make this, so I guess I have written this. Did I write this down somewhere? What is it all about? No, but I just say it here. So machine learning is about finding the best hypothesis out of a huge set or space of possible hypotheses. And this space or hypothesis space we call model. Each machine learning method uses a particular choice for the model. There are linear models, there are decision trees, there are artificial neural networks. These are all different choices for this set of possible hypothesis maps. Okay, but to make this principle something practical, or that we can implement somehow program, we need to measure how good is a hypothesis. And here comes the loss function. This is our third component. After data, after model, we need a loss function. So we need some measure that quantifies the errors that we make. We typically make errors. If we would predict everything perfectly, then it would be boring. And then there would be not much to do for a machine learning scientist or engineer. We always make errors. The only goal is to make the errors as small as possible. But we need to measure the error. We need some measure. And this is exactly a loss function. So this might sound a bit abstract, but again, like the notion of data points, features, and labels, it's a very versatile concept, but we need to practice it by looking at special cases, at examples. So one example of a loss function that is very popular for labels that are numeric, like numbers, like the maximum temperature. So one very widely used loss function here is the squared error loss. So what do we do to compute the squared error loss? Well, we look at a certain data point. So we have some data point, a certain day. And we know that the feature, like the minimum temperature, would be -5 degrees. And let's say it was a previous day. So for a previous day, we can look up the weather recordings from the Finnish Meteorological Institute, and we know that the maximum daytime temperature was 0 degrees. Okay, so this is one data point for which we know the label value. And this is sometimes called a labeled data point. The more of these labeled data points we have, the better. But typically, it's difficult to get these labeled data points. And now we have some hypothesis. Let's say our hypothesis is that the maximum daytime temperature is 2 times the minimum daytime temperature. So this is our guess. And for this data point, this would mean that our predicted maximum daytime temperature would be 2 times -5 would be -10. Okay, so this is our predicted maximum daytime temperature, but the true maximum daytime temperature would be 0. So what do? We compute -10 minus 0, which is -10, and square it, and then we get a value. In this case, the loss would be 100. So a loss is again a map, like a hypothesis, a map. This is maybe the only mathematical concept we need in this whole course, the concept of a map, a function. In this case, the loss takes as input a data point for which we know the feature and the label value. So here -5 and 0, and a hypothesis. So the hypothesis is here a linear function that multiplies the argument by 2. So a loss, formally a loss is a function that reads in a data point, which has a feature and a label value, which we need to know. Otherwise, we cannot evaluate the loss. And a hypothesis map. So some candidate for the hypothesis map. In this case, we have this hypothesis map. It's one possible hypothesis map, and we get a number out of it. So for this example, this number is 100. So we have defined a rule that reads in a data point and a hypothesis and outputs a number. Okay, but this is only one option. Another option is an absolute error loss. So we could use the absolute value of this difference between predicted label and numeric label. Yeah, but be careful. This loss function only makes sense if these symbols here make sense. So only if we can take a difference, because if the label values, and remember, the labels is a design choice, and also the values that the label takes is only a design choice. So the label value could be, for example, either cat or dog in a classification problem, in an image classification problem. Cat or dog. So in this case, it doesn't work. So what does cat minus dog mean? What does this give, cat minus dog? Fur or hair? I don't know. We can only take the difference between numbers. So this absolute error loss and the squared error loss, we typically use for numeric label values. And we call such problems regression problems. Okay, so now let's look at a classification problem where the label could be either cat or dog. So how do we define a loss function here? Well, we could say we could specify the loss for all possible combinations of true label. So let's say the label values are either cat or dog. Yeah, I'm grateful for any hints what to use to annotate the slides on a MacBook. Is there some trick to use an iPad to draw? Please let me know by email. I would be very grateful. Because now I'm really having a hard time with using the the MacBook trackpad for these annotations. So, but let's now define a loss function for this. So we could say here the columns are the possible values of the true label, and the rows represent the possible values of the predicted label. So here we have cat, here we have dog. Here we have cat, here we have dog. And then we just need to specify for each possible combination a number. So let's say if the true label is cat and the predicted label is cat, would we like to have a large loss or a small loss? Small, yes, because this is we call this a correct classification or a correct prediction. Yeah, so small. So if we have the true label, so it's a cat image, but we predict dog, then we want a large loss because we don't want that. So let's say if the true label is dog, so it's a dog image, but our classifier, our predictor, this function here, outputs dog. So it's again a correct, so let's again 0. And then let's say the image is a dog image, but there are a classifier or a hypothesis here. So we call a hypothesis if it outputs a value from a finite set. We call this sometimes classifier. But I would not be too picky about these notations. In the end, classifier, a hypothesis, or a predictor, these are all just maps that read in the features of a data point. In this case, the features could be the pixels of the image and output a prediction for the label. So let's say now the true label is dog, so it's a dog image, but our classifier outputs cat. So again, we would like to have a large loss function, but there's no need that these loss functions are the same. So it's a design choice. So this table here that I'm drawing is up to you. So if you prefer dogs, some people prefer dogs, in particular in the east of Helsinki, a lot of dog lovers, it seems. And then we would like maybe to be very critical if a dog image is classified as cat. So there's a very large loss. Yes, so it's up to you. And a less funny example, I supervised a master thesis recently where the student had to build an object detector or a person detector for harvesters. So, you know, Finland has a lot of forest and they use big machinery to cut the trees. They make it very quick, but it's dangerous if there are people nearby. So, and the goal there was to detect, is in an image a person or not? And there, the different cases, so if there's no person in reality, but the detection is person, this means just a false alarm. It can happen, but it's not too problematic. But what you would really like to avoid is there is a person and you don't detect the person. So you would have a much, much higher loss for this error type. Okay, so yeah, and what I would like to point out here is some kind of sloppiness in our notation in general, and it would pay off if you take the pain in the beginning and get used to this. So even if we have data points which have only two different label values, like cat or dog, it makes sense to use as a hypothesis map a function that outputs a number. For example, a real number, like a linear map. So it still could make sense. And we do this actually in a method called logistic regression, which you will hear about next week in next week lectures. So it could make sense to use a function of this form. So the features, let's say the features are a numeric vector or a NumPy array, if you implement it in Python. And you multiply it by some weight and add, so W times X, X plus some other parameter, W1. So some linear function. It still can make sense to use such a linear function to predict the label, which can only be cat or dog, because you can always threshold. So you can always, in the end, do a hard decision or classification. So you can always say, okay, if this hypothesis value, the value of the hypothesis map is larger than 0, you classify the image as dog. And if not, so if it's smaller or equal than 0, then you classify it as cat. So you can always easily then threshold a real number. So let's say this would be a real number, this value, this predicted value, the predictor value. You can always threshold it and get a predicted label. But what is more, because you use a real number, you can also use the absolute value. And it turns out to be a very good idea to use the absolute value of such a linear function, for example, as a confidence measure. So what do I mean by a confidence measure? You could interpret this absolute value as how certain are we, or is the classifier in, for example, the image being a dog. So you could have the hypothesis being 0.1, or the hypothesis being 10 to the power of 6. Both of these values for the hypothesis would be larger than 0 and result in a prediction dog. But in this 0.1 case, you would be way less confident in the prediction than in when you have the predictor value 10 to the power of 6. And you can use this confidence measure then to design a loss function. In particular, the logistic loss that is used in logistic regression takes into account the confidence. So even if you have the same output prediction, dog, depending on the value, on the absolute value of this linear function, the loss is different because you want to penalize that what you really want to penalize. I guess I have here a nice, here I have this, this plot. So let's say we have a data point here with some feature vector x and a label value, quantity of interest being, so what do I have here? Y equal to 1. So we have a data point for which we know the features, like the pixels of an image, and we know it's category 1. Let's say this category 1 could represent dogs, but it doesn't matter. So there are just two categories, -1 or +1 here in this case, as this is a binary classification problem. So what does this mean? Let me now walk you through this plot a bit. On the horizontal axis, I draw the values, the possible values of a hypothesis that is applied to this feature vector. So we have a certain hypothesis given, like a linear function. So this W transposed times X for some parameter vector W. So we look at a certain hypothesis and we study what should be the loss incurred depending on this function value, on this hypothesis value. So let's look to the right. So on the right, the function value is larger than 0, which means we would predict the label would be, or the predicted label is 1. Okay, this is good. So this is a correct decision. So on the right side, we have only correct decisions. Whereas on the left side, for every hypothesis that delivers a negative value, we would predict y hat equal to -1, which is a wrong prediction because the true label, we start from the assumption that the true label is 1. And if we predict -1, this means wrong, classification. Okay. So everything on the left of the vertical axis is a wrong classification, corresponds to a wrong classification. Everything on the right, correct. So one loss function that I showed here, it's called the 0-1 loss, and this is maybe the most intuitive. It just penalizes wrong classification. So as soon as this hypothesis h of x is smaller than 0, which mean we threshold it and we make the prediction y hat -1, but the true label is +1. So it's a wrong prediction. So everything on this side would mean loss equal to 1. Everything on the right side, which means a correct prediction, would mean loss 0. So wrong prediction, wrong classification ends up in loss 1. Correct classification ends up in loss 0. So this seems very intuitive. However, it's statistically not a good idea. We throw away information in some sense here, because we really would like to avoid at all costs to have a wrong classification and to be very confident in a wrong classification. This means if we have h of x negative, but very much negative, this means we do a wrong classification because it's smaller than 0, but also we are very confident in this classification, which is wrong. And this is exactly what we want to penalize. This is also in general when you are studying or for students, when you are unsure, it's better if you say it, I don't know. So in the classification case here, this means if you're unsure, then it's better if the output of your classifier is around here, which means the absolute value is around 0, which means very low confidence. What is really bad, if you say something, or if you output a wrong result and you are very confident in the wrong result. So, and this is what we would like to penalize. And this is done by other loss functions, which are different than the 0-1 loss. One of them is called the logistic loss. You will hear more about this in the next week's lectures about logistic regression. And another one is called the hinge loss. This loss function is like a straight line on the left. It passes through 1 in the vertical axis and goes to 0 at +1. And then it stays at 0 forever to the right. So, but they are not too different. Well, there's some difference because this logistic loss is a nice smooth curve, and maybe some of you already know about optimization methods, and such nice smooth curves we can always minimize by making little improvements, little jumps down a gradient. So we can use something like gradient descent, but we will not talk more about this gradient descent methods. This is topic of advanced machine learning courses. We will mainly use ready-made minimization algorithms. Okay, so here I show 3 of the most commonly used loss functions for binary classification problems. The 0-1 loss, which seems very natural. So loss 1, we use loss 1 if we make a wrong classification, loss 0 if we make a true classification. However, it wastes information. It's statistically not optimal. It's better to use a loss function that grows with the confidence in wrong classification. So this logistic loss grows faster and faster, actually, for wrong classifications, for very confident that are made with a big confidence. However, on the other side, if the decision is correct, it becomes more and more irrelevant how much confident you are. So you can be confident with 2 or with 100. It's not much difference. But what is really important, the more confident you are in a wrong classification, the stronger should be the penalty. The stronger should be the larger should be the loss. Okay. Yeah, so to wrap up this block, like the data, what you use as data points, what you use as features, what you use as label, is the loss function is also a design choice. So there are different basic types of loss functions that are widely used, and there's a lot of understanding of them. But in principle, you can construct the loss function yourself. So for the binary classification case, remember here, we can design these table entries. This table defines the loss function. So you define the loss function by filling out this table, and you can choose those values according to your preferences or needs, business needs in the application. Okay, so what are the aspects one should take into account when choosing a loss function? Well, of course, we would like a loss function to be reasonable in the sense that you really would like to learn a classifier that is accurate. So in the end, when you evaluate a classifier, what you would typically like to have is very low probability of wrong classification. So in the end, you might want to use this 0-1 loss for a final performance evaluation. So any loss function that you choose then for finding a good hypothesis should be somewhat similar to the 0-1 loss. However, the 0-1 loss is not good statistically because you throw away this information of large confidence in wrong classifications. So there's some statistical how should I say, trade-offs, how you choose the loss function. Actually, one principled way to come up with a loss function is to set up a probabilistic model for data, which is beyond the scope of this course. I just pointed here out. One way to design a loss function or to come up with an educated guess for a loss function is to set up a probabilistic model. And this probabilistic model involves then expressions for probability density of data that you observe. And these expressions, they can be used as loss functions. And this is actually used in a principle called maximum likelihood, which you can read more about in my textbook. So statistical aspects can be used to come up with a good loss function. Then also very important, computational aspects. You need to search over a large hypothesis space, which is much larger than this one here. This here consists of 2 possible hypotheses. So learning the best hypothesis here means compute the loss or the average loss averaged over all of these data points here for this hypothesis and for that hypothesis. So for 2 hypotheses and pick the one with a smaller loss. So that seems pretty much straightforward, but in reality, we use hypothesis spaces which have infinitely many hypotheses. So we need to be able to evaluate the loss function quickly. And there are some loss functions which allow this, like the squared error loss, or also the absolute error loss, because they have a property which is called convexity. But don't worry, we will not go into any more detail about convex optimization in this, but you can find the advanced follow-up courses on this in the related courses section. yes, so computational aspects are important, but also, and this is should not be overlooked, the interpretation, because when you then look at the log loss, so you can compute the log loss, and you will do it in one of the assignments, you get a number. So you get, for example, here 1.2. But what does that mean? So to be honest, I would not be able to interpret this really well. What does log loss of 1.2 mean? But what I can really nicely understand is this 0.1 loss, or the average 0.1 loss as a percentage. So let's say 10% of all the data points have been classified wrong. Okay, then I know error rate 10%, or 1 minus error rate would mean 90% accuracy. So accuracy is essentially equivalent to the 0.1 loss. It's just 1 minus average 0.1 loss. This is the accuracy, and this is what you typically would like to provide in a data sheet of your app, of your classifier. Look, I developed a classifier which achieves accuracy 99%. So for the interpretability, you might prefer the 0.1 loss. However, the 0.1 loss is not good from the statistical aspects, and also not very handy from computational aspects, because it has this discontinuity here around 0, and minimizing discontinuous functions is very hard. Okay, yeah, I just want to point out here, this choosing a good loss function is far from trivial. And one of my recent master students, which did an excellent master thesis, so one of the main contributions of his thesis was to come up with a good loss function for an application where they want to detect persons from drone videos, because in search and rescue missions, you have to screen a large areas in the countryside. And for these applications, you need a specific type of characteristics of loss function. And he came up with a very useful one, which is the main content of an academic paper. Okay, so I would suggest we have now a little break. I will also try to answer some questions. Let's say we meet again at 5:05 p.m. So welcome back to our lecture. Can you hear me, and can you see the slide empirical risk minimization? Yes, thank you. So yeah, there were some questions now about how could we better illustrate these theoretical concepts like loss function and so on and so forth. I think for this reason, we have these coding assignments. So please be a bit patient and work on the coding assignments, the first 2 coding assignments, and you might get some revelation how these rather dry concepts that I'm talking about now work out in practice. Okay. So now for the main part of this lecture today, actually, after we have now introduced all these 3 components of machine learning, data, a model, and a loss, so how do we now combine them? And this is done using the notion of empirical risk minimization. So what I now want you to tell or to teach you is, first of all, to know about the concept of expected loss or risk. So we need a bit of probability theory, but only as much as really required for our purposes. And then we will see that we can approximate this notion or this quantity called risk using average loss in particular. And this average loss we also call empirical risk. And it seems quite natural to try to minimize the empirical risk. Yeah, so, but again, also in this empirical risk minimization, we have design choices. So we have design choice data, the design choice of model, and the loss. And we will discuss a bit what are the effects of these design choices on empirical risk minimization. So to remind you again, we have data, which is a set of data points. Each data point is characterized by features X and a label, a quantity of interest Y. We have a model, a machine learning model, which is a set of hypothesis maps. And we now also have a loss function that tells us how good is a certain hypothesis when predicting the label of a data point. So as an example, we could have data points being days. So here one day, the 1st of February 2020, another data point would be the 2nd of February 2020, and each data point has several features and label. So we could choose, for example, as feature the minimum temperature and as label the maximum temperature. So we might stack them into also a feature matrix. We call this a feature matrix. So each data point here, just to make you familiar with this notation, how to map these data sets into matrices and vectors. So each data point here is denoted here by one pair of feature and label. So the feature of the first data point is here the minimum temperature. So this is this here, and the label would be here the maximum temperature of the first day. Then we have the minimum temperature of the second day would be the feature of the second data point, and so on and so forth. And it's convenient to stack those feature vectors. So in this case, these are single features, so scalar features, into a feature matrix. And also to stack the labels into a single vector. Yeah, so now the name of the game in machine learning is find me the hypothesis with the smallest loss on a data, incurred on a data point, in general, on any data point. So we want to find a hypothesis that does good for any data point that comes in. So I want to learn a hypothesis that is able to read in the minimum temperature of a day and gives me a prediction for maximum temperature for any day. But what exactly do we mean with any data point? So we need to somehow make this more precise. So we want to have a hypothesis that incurs a small loss. But the loss, again, the loss depends on, where do we have the loss? The loss depends on the hypothesis. So this is something we will try out, different hypotheses. This is what machine learning is about, try out different hypotheses, such that the loss here is as small as possible. But the loss depends also on the data point. So how can we find a measure that applies to all data points? And one approach to solve this conceptual problem or challenge is to use probability theory. So we could say, we think of the data points that we observe, like this here, this finite list of data points. These are just a few examples of an underlying population of infinitely many data points. And such a population is what we can characterize so statistics is the study of such populations. And how can we study such populations? How can we characterize their properties? Well, with something called the probability distribution. So maybe some of you have heard about Bernoulli probability distribution or Gaussian probability distribution. These probability distributions basically specify the density of how many data points are in certain areas in the space of feature and labels, possible feature and label values. So we can characterize such a big population or an infinite population using a probability distribution. And we can then say, or we can interpret the data points that we observe, like the data points that we read in from a CSV file and that you will read in particular from a CSV file in the coding assignments. This finite list of data points, these weather recordings, these are just realizations, some of the realizations of this probability distribution. So every time we get a new data point, we start our random generator and we draw one realization of this probability distribution. Okay. And as soon as we introduce such a probability distribution, what we can do is we can define an expectation. We can compute an expectation. So we can now compute, in some sense, the average over all possible data points. So this is what this expectation is in the end. It's an average, but a very fine-grained average. It's an average over all possible realizations, and these individual losses, they are weighted by this probability distribution. Okay, but don't worry, don't be scared now of this math notation. We will not go into any more details. You're not required to do probabilistic calculus in this course. It's just meant to give you some motivation for what comes next. So it seems to be a good idea then to, okay, so now we have a measure that tells us how well is a hypothesis doing on average for all possible data points, if we know the probability distribution. So this is important here. To compute this risk, we need to know the probability distribution, but you never know the probability distribution in reality. All you know in reality, all you get in reality is a finite list of data points. You never know what the underlying probability distribution is unless you generate these data points using a random generator, using some simulation tool. But if you get this data from the Finnish Meteorological Institute, who knows the probability distribution underlying this data? So it's just a modeling assumption, but it's a very useful modeling assumption. Or in some sense, it's a hypothesis. It's a higher level hypothesis that there is some underlying probability distribution and we can define the risk. However, we don't know this probability distribution. So what do? One very powerful trick in general, when you have a set of realizations of independent random variables that are all distributed according to the same probability distribution, and you want to know some expected value, then just you can approximate this expected value using the average. So we approximate this risk using the average of these individual losses. So this term here in the sum, this is the loss incurred by a given hypothesis on the ith data point. So for example, if I is 1, this would be the loss incurred for the first data point. Or for the last data point, this is the loss incurred for the mth data point, if we denote by m the number of data points. And if it can be made precise, if this m, this number of data points in this data set, or we call it sample size, if this is large enough, then this becomes a very good approximation of the expected loss, or the expectation here, or the risk. And this average loss is what we call empirical risk. So this empirical risk is the average over all losses incurred by a hypothesis on a finite set or sequence of data points. And the sequence of data points might be, for example, these days that you read in from the Finnish Meteorological Institute. So each row here is one data point. Some of the properties in this row we use as feature. Some of the properties we know as label. We use as label. And so now that we have defined the empirical risk, well, it seems natural. Ideally, we would like to find a hypothesis that has minimum risk, but we cannot compute the risk unless we know the probability distribution, which is rarely the case. So what we do, we minimize the approximation of it. We minimize the empirical risk. And this is what I denote here by L hat. So there's bit of notation now coming in. So this is something I guess you need to work through, unfortunately, but it's helpful in what follows and convenient. So yeah, you see this equation numbers here, they refer to the course book. So you find those in chapter 2, I guess, this equation. Yeah, the important point now here is what we minimize, empirical risk minimization, is this average loss on the training set, or the empirical risk. So this is the average loss or training error, but what we would like to minimize actually is the risk. So this is the one important point here that separates theoretic optimization or plain optimization theory from machine learning. In machine learning, we would like to optimize the risk. So we would like to tune this hypothesis, try out different hypotheses, and find the one with the smallest risk. But we cannot compute the risk. We cannot evaluate the actual objective function. which is indicated here dash dotted. Instead, we need to minimize an approximation to this objective function, which is the empirical risk. So we cannot minimize the objective function, but we need to minimize an approximation of the objective function. And this sets machine learning apart from general optimization theory because, for example, it doesn't make too much of a sense to find really the optimum here or to find a hypothesis. Let's call this hypothesis H1 that has minimum empirical risk, because actually what we now do is we increase the risk. This is referred to as overfitting, by the way, and we will spend a lot of time in the following lectures to find out when is overfitting happening, when can we detect overfitting, and how can we avoid it. So this is maybe one of the takeaway messages from today. In machine learning, it's rarely necessary to perfectly optimize the objective function, which is the empirical risk, since it is only an approximation of the actual objective function, the risk, which I'm interested in. Okay, so now I've written here together empirical risk minimization for parameterized models, or for a set of hypotheses which are characterized by a parameter vector W. One example is a linear map. So this linear map is, each linear map is parameterized by a parameter vector, W transposed. So you can think of this parameter vector as the ID, as the social, like in Finland, you have a social ID. The ID fully identifies you. So if you know the ID, you don't need to know like anything else, the passport number or something. And similar here in a parameterized model, all we need to know is the parameter values, and we know the whole function. So instead of optimizing over functions, we can optimize over parameter vectors. It sounds, wow, cool. Now we optimize over parameter vectors, but remember, still, this is an infinite space. It's the space of all vectors of length n, for example. Still infinite, but it has a bit more structure, which is nice for optimization. Okay, so again, now I just draw this picture for empirical risk minimization using the parameter vectors. So what we learn, what we tune, what we try to optimize is a parameter vector here for a parameterized hypothesis space. Does any one of you know another example of a parameterized hypothesis space besides these linear functions? Do you know another set of possible hypotheses that is characterized by parameter values? I have talked about in the first lecture on Monday. Polynomials, yes, polynomials. They are parameterized hypothesis space. What else? Something that is very cool in the last few years, a tiny subfield of machine learning, artificial neural networks, deep learning. So deep learning also uses parameterized hypothesis spaces or parameterized models. Okay, so and just to remind you, here in this empirical risk minimization, we have 3 design choices to make. We have, of course, the design choice to get data. Where do we get data? How do we define data points? What do we use as features? Do we use the minimum temperature as the feature, or do we use the temperatures of the previous 3 days as the features? It's a design choice. What do we use as loss function? Do we use the squared error loss? Do we use the absolute error loss? Design choice. What do we use as model? Do we use linear functions, polynomials? All design choices, and they have effects in several regards. First of all, they have an effect on how quickly we can solve these optimization problems. And second, what is the discrepancy between these minimizers? So what we really would like to have is that the minimizer of the risk, which is really what we would like to minimize, and the empirical risk, that these distances, they are not too large. So this is somewhat close by, which means that in more technical terms, the machine learning method generalizes well, or it's not overfitting. If this distance, if this move apart from each other, a large, so this means that what I actually minimize, the empirical risk, is a super bad approximation of the actual risk, then what you will get is basically nonsense. Then you will not learn a good hypothesis. So this should be close. This should be really tied close to each other, these 2 minimizers. And how far they are apart to some extent depends on the data, on the loss, and on the model. Okay, so let's now look at the effect of the model on the empirical risk minimization. So remember, in linear regression, what we do is we use as model the set of all linear maps. So the model or hypothesis space is the set of all hypothesis functions of this form. We have some parameter vector and take the inner product with the feature vector x. And we try out different parameter vectors. So here we get another one for another parameter vector. Here we get another one. And we compute for each of these choices the squared error or the average squared error on some training data set and try to minimize it. So I have now written this out. So empirical risk minimization for linear regression looks like this. So we use the design choice for the model linear functions. So this is here is the design choice for the model linear functions, and we use the squared error. This is the design choice for the loss. So this results in a particular instance of empirical risk minimization. And you will do this in, I think, in assignment 2. So how can you implement this? You don't need to solve this optimization problem on pen and paper, but you rather use here 2 lines of Python code. So you call a .fit function. This class here, linear regression class here, this provides methods to search over the set of all linear maps. So this linear regression class kind of embodies all the properties of the linear model. And one of these properties is, or one of the functions of this linear model is to find the linear map within the set of all linear maps that have the smallest, average squared error on a training set. And how do you tell it? How do you tell Python what the training set is? Well, these are these 2 parameters here. Features, this is the feature matrix. You have to form this feature matrix in a few lines above. So this is typically the anatomy of machine learning Python code is often the same. So in the beginning, you have some data processing. You read in data from a CSV file. You read out the features of the data set or a data frame. We call it data frame in Python. And we stack this into feature matrix or in Python. What do we use in Python to store a matrix or a vector? What is the main data type within this course? The main Python data type to represent the matrix or vector, which are just arrays of numbers or numeric arrays. Any guesses? NumPy arrays. Yes, NumPy array. Very good. So these features is a NumPy array that represent, the NumPy array is the Python variant of a matrix or vector. Okay, so this seems pretty much straightforward. And then what you do is, so what you get out of this .fit function is you get the best parameter vector, and this optimum parameter vector W is stored in this property .coef. So what this gives you is this here, this point here, this optimum parameter vector, which has the smallest objective function. And this objective function here, this minimum objective function, is the average squared error you get from the optimal predictor or optimal hypothesis. And this is what you can evaluate using this mean squared error function. This is this point here, this number here. Okay. So, but then, of course, you might think, okay, linear regression, it seems so simple, but don't be mistaken. Linear regression is very powerful because you can upgrade any linear model using new features. So this is also a funny word game. Here, you can upgrade the linear model with new features by using new features, by constructing new features. And how does that work? Well, for example, nobody can keep you from, for example, taking here the minimum temperature, which is the raw feature in some sense that you get from the Finnish Meteorological Institute, and then computing the square, or computing power to the 3, or computing power to the 4. Everything that you can compute easily, you can use as a feature. Why not? And but this can be done very conveniently in Python using this function here, polynomial features. And this is what you will use, I guess, in assignment 2. So you use this function polynomial features to start with a single feature like the minimum daytime temperature and compute a whole bunch of new features like the powers of this minimum daytime temperature. So if the minimum daytime temperature would be 2, then you get as first feature, I think this is x to the power of 0, which would be 1 in any case. Then the next one would be x to the power of 1, which would be 2. Then the next one would be x to the power of 2, the next feature, which would be 4 for this example. And you get a bunch of new numbers, which are new features. And these new features you feed into a linear model. And what you get overall, if you concatenate this feature map and the linear map, is a polynomial regression. So polynomial regression is equivalent to first doing a feature transformation, computing the powers of the raw feature, and then stacking it together with a linear model, then applying a linear map. Then you get polynomial regression. And so polynomial regression per se uses as model as the space of possible predictor functions or hypothesis maps uses polynomials. So here Georgios or TA Georgios prepared a notebook where I put the link here. You can find this notebook under this link on my GitHub repo, where you see a few of these example hypothesis maps. So the model of polynomial regression with degree 2 is the set of all polynomials with degree at most 2. And here a few of those hypothesis maps are depicted here. Yet another model, so this is now a different model. It's the model consisting of all polynomials of degree 6. So this is a different model. Are these two models related? So this here is one hypothesis space. I used to denote this calligraphic H and superscript 2. So this is one model. It's the set of all polynomials with degree at most 2. And this is the model consisting of all polynomials with degree at most 6. Are these somehow related, these two models? What is your guess? Yes, so they are related because this is a subset. The polynomials of degree at most 2 is a subset of polynomials of degree at most 6. Quite clear. So let us look at what happens in this empirical risk minimization if we use larger and larger models, like use polynomial regression with larger and larger degrees. So this here would be polynomial regression with degree 1. And this here would be polynomial regression with degree 2 and here with 3. So what we do is we make the optimization domain. So the hypothesis space is used as optimization domain in empirical risk minimization. We make this larger and larger. And when you minimize over a larger domain, the only thing that can happen is you get a smaller objective function or optimal value of the objective function. So these training errors will go down when you increase the polynomial degree. However, which model is the best? Is the best then to take the as large model as possible? What do you think? No, why not? What is the ultimate goal? Well, the ultimate goal is to find a hypothesis that does well on any data point. And one way to make this precise is to say that does well on any data point on average or in expectation. So we want to make the risk as small as possible and not mainly the empirical risk. The empirical risk is just a proxy, an approximation. And when you use a larger and larger hypothesis space, what you will do is, of course, you will get smaller and smaller training error for 0 almost. However, the resulting hypothesis becomes less and less useful because the deviation between the minima of empirical risk and actual risk gets larger and larger. So you will overfit. And we will then learn in later lectures like model validation and selection, how to detect overfitting using a simple method called validation and how to avoid overfitting. This is something we can do with regularization techniques. Yes, so, okay. Maybe let's have a quick break now before the last stretch about the loss function. So let's meet maybe in 5 minutes again. I will try to answer some questions again. So 5:35, 7. Okay, so let's finish this up now. Before I start with the final stretch on the loss function, let me quickly go back. So can you see my slides? Yes, thank you. So yeah, there was one question, very good question. So what is now the best hypothesis actually? The best hypothesis space or model in this case? What is your guess? What is the best one here? Hypothesis space 2, yes, because if we look at the weight, the parameter vector that is learned here, so when we minimize the empirical risk, which is this curve here, for model 2, we end up here at this point. And if we kind of look then up the risk of this hypothesis with this, so let's say this would be parameter vector superscript 2. This is the one which we learn when we use the model, or let's say the polynomial regression with degree 2. We end up here. This would be the one that we learn with polynomial regression degree 3. And if we look at the corresponding risks, so here this optimal weight vector for degree 3, or optimal in the sense of empirical risk, is very suboptimal in terms of risk, whereas this weight vector here is almost the optimum weight vector for the risk. So in this case, it's model 2. However, can we do? Is this a practical recommendation now? So that we found out that this model 2 is optimal. The way how we found it out, is this something practical that I now demonstrated? This selection. Can we do this in practice? No, because in practice we do not know the risk. I know the risk only because I hypothesize it here. So in practice, you don't know the risk. That's the problem. However, we will then see in model validation, we can somehow estimate the risk. Or particularly, we can estimate the discrepancy between the empirical risk or the training error and the actual risk. That's what model validation is about. More about this, I think, in 2 weeks. Okay, so now the final stretch of today. What is the effect of the loss function on the empirical risk minimization? Remember, the loss function is a design choice. So in principle, we can use any rule that takes in a data point with feature X and label Y and a hypothesis and outputs a number. So, or in particular, it might only depend on the prediction error. So this Y hat is here, is the output of the hypothesis map. But there are also loss functions that cannot be written as a function only of this error. So in particular, the logistic loss that you will see next week, it depends in a more complicated way on the hypothesis. So it's not always possible to write the loss function as a function, directly as a function of the prediction error. However, for those which I will now discuss, it is possible. So the first one would be the squared error loss. What is the advantage of the squared error loss? Why is it used as the first choice, I would say, as the first tryout for numeric label values or regression problems? Because it can be minimized so easily. It can be minimized so efficiently. For example, using gradient descent. However, there is some caveat with this squared error loss. In particular, it's very sensitive to outliers. So it might be, for example, that in some of the data points in your training set, something went wrong with the temperature measurements. So something went completely off. Let's say here we measured 30 degrees in February in Finland. There was just an error in the sensor in the temperature measurement. So that this is called an outlier. And if you have only one such outlier in a data set that is not too large, so only few outliers can really mess up the learning when you use the squared error loss. So they have a strong effect on the learned hypothesis. So one outlier. So let's say here we have clean data. So there's no error. We get good. We get correct temperature measurements from the Finnish Meteorological Institute. Each dot here represents a day with minimum temperature X and maximum temperature Y. And and we then learn a linear predictor by minimizing the average squared error, okay? So we get this curve. Let's say we get this dashed curve. Now let's say we have one single outlier, one measurement was off, and then minimizing the average squared error results in the resulting predictor to be completely different. So only having one corrupt data point in a training set results in the solution of empirical risk minimization to be significantly different. So this sensitivity to outliers is not something that we like. So how can we make this more robust against outliers? There are different options. So what would be your suggestion? How can we avoid the effect of outliers? What is a trivial approach? Well, the most trivial approach would be to look at the data set and say, yes, deleting it, removing it. This is sometimes called cleaning data. So you look at the data set and there are some data points which are completely off. But they do not conform with this assumption that each data point is a realization of a random variable with the same distribution. So these data points, they violate this IID assumption. So one option could be try to get rid of them. Just look at the data, and this is called anomaly detection. However, there's a somewhat neat alternative to this, which is use a different loss function. Use a different design choice for the loss. In particular, if you use the absolute error loss, and you will just try this out by yourself, you will see it by your own eyes in assignment 2, what the effect is when you have an outlier. Because when you minimize this absolute error loss, the effect of the outlier will be much more smaller. So you train the model on clean data by minimizing the average absolute loss, absolute error loss. You get some predictor, some hypothesis map that has minimum average absolute error loss. And then you train it again on this corrupted data set with one outlier, and you will see that the resulting learned hypothesis is only differs very little from the one that you get when training on the clean data. So using this absolute error loss brings a lot of robustness or can tolerate the presence of a few outliers. So let me give you some intuition why this is. The squared error loss grows very fast. So most of the data points would be here, would have prediction errors here, this clean data set. However, there might be one outlier here. And this outlier is, the effect of this outlier is amplified because the loss gets squared, or the prediction error gets squared. So this squaring of the prediction error, the square, amplifies the effect of a single outlier extremely. However, if we take the absolute error loss, the effect is not so strong. It's only linear increasing in the magnitude is only linear increasing in the magnitude of the prediction error. So it's much less emphasis on this single outlier. Okay, so this absolute error loss makes the resulting empirical risk minimization method more robust against outliers. And I just want to point out that the squared error loss and the absolute error loss, they can be generalized to something that is called the Huber loss. So the Huber loss is kind of a blending of the absolute error loss and the squared error loss. It is defined by having the squared error loss for small prediction errors, because we assume that these prediction errors, they arise for the clean data, for the bulk, for most of the data points which are not outliers. So here we use the squared error loss, which is nice to optimize or fast to optimize. But then outside this tolerance band, I would say, we use the absolute error loss because we want to de-emphasize the effect of a few outliers. So here we would have an outlier, and that's why we want to not use the squared error loss that far out for that large prediction errors. Okay, so the Huber loss mixes the absolute error loss and the squared error loss. And it's, of course, nicely implemented or ready-made in Python. And you will find here this parameter epsilon for this class Huber regressor. So Huber regressor is obtained by using the linear model, so the set of all linear functions, which is also used by linear regression. But in contrast to linear regression, in Huber, the Huber regressor uses the Huber loss. So choosing a different loss results in a different machine learning method, with different properties, with different statistical properties and computational properties. So if we now compare the squared error loss and the Huber loss, the squared error loss, what is very pleasant about it is results in a convex and differentiable objective function. So something that we can minimize easily by jumping down the gradient of this function, loosely speaking. So we can do this with gradient descent. The Huber loss, on the other hand, it has some corners in the objective function. And these corners, this is then called a non-smooth function. They prohibit that we can use this simple technique of jumping down the gradient, because we might overdo. We cannot extrapolate. We never know. In some sense, we don't know where these corners are. So we have to be more careful. We can only make smaller progress in each iteration, and which means we need more iterations. But this is just a high-level discussion. We will not go into any more details of non-smooth optimization. This is the subject of advanced master-level courses on optimization theory. But just to point out here, these two different design choices for the loss, the squared error loss, which is used for linear regression, and the Huber loss, which is used in it's sometimes called robust regression or Huber regression or Huber regressor. They have different computational properties. Huber is a bit slower, and statistical properties. So the Huber loss results in the overall machine learning method to be more robust against a few outliers, whereas the squared error loss is highly sensitive to outliers. This is really messed up. If you have a few large outliers, squared error loss doesn't give you nice results. However, there are other options to get rid of outliers, as you have pointed out on the chat. Try to spot them somehow using some anomaly detection methods. But I think we will only briefly touch these anomaly detection applications later in later lectures. Okay, so this brings me now to the summary of today's lecture. We have started with defining the ultimate quality measure for a hypothesis, which is the expected loss or the risk. So it's the average loss over all possible data points. And the possible data point is any data point that can be obtained as a realization or a draw from a random variable. And this random variable has a certain probability distribution, which we would need to compute, to actually compute the expected loss. So we typically never can compute the expected loss, but we would like to make it as small as possible. And to resolve this dilemma, we use the risk, or we use the empirical risk in the form of the average loss over some training set to approximate the loss. And if this approximation is good enough, we can minimize this empirical risk and get a hypothesis that has a small risk. But sometimes this doesn't work. And one case where it doesn't work is called overfitting. So there are situations called overfitting where minimizing the empirical risk does not mean anything that you get for having a small risk. So a large part of this course will be on methods or techniques to find out if this empirical risk is a good approximator for the risk, and if not, what can we do? We always have these design choices for loss function, model. We can select different models or try to get more data. So data is also a tuning knob by, for example, collecting more training data in order to make the empirical risk a better approximation of the actual risk. Yeah, and I would say any method that you hear about in this course is an instance of this empirical risk minimization problem. So any machine learning method we teach you in this course is an optimization method. So if you have good knowledge about optimization, you can do better machine learning. And we have pointed out in the related courses section some advanced courses on optimization. So the details of optimization algorithms is beyond the scope of these papers. This course. So we use the .fit function in Python for solving these optimization problems. Okay, so that's all I had in mind, and I now try to answer some questions on the chat. Yeah, but first, let me point out, please continue working on assignment 1. If you have any questions regarding the assignment, start looking at the frequently asked questions on the My Courses page. Then contact us or look at the current questions already on the Slack discussion forum. Then you have always the opportunity to reach out to us by email. Do not hesitate to contact us. We are there to help you to learn to achieve the learning goals of this course. Yeah, and the next lecture will be next Monday on classification methods. Thanks a lot.